This question is called random ants. It says 500 ants are randomly put on a 1 foot string, independent uniform distribution for each ant between 0 and 1. Each ant randomly moves toward one end of the string, equal probability of being to the left or to the right, at a constant speed of 1 foot per minute until it falls off at one end of the string. Also assume that the size of the ant is infinitely small. When two ants collide head on, they both immediately change directions and keep on moving at 1 foot per minute. What is the expected time for all ants to fall off the string? Okay, cool. So we're trying to find some expectation. We have some string from 0 to 1. There's ants placed on the string randomly. And since we're given a hint here, independent uniform distribution, so we're saying these are random variables. So we can say each ant is some random variable, and there's 500 of them. They're all uniform. They all follow uniform distribution from 0 to 1. Okay, cool. Now, there's two important factors here we have to consider. The fact that when they collide head on, they change directions, and the fact that they move to the left or to the right. So first things, let's consider the collisions, right? If we have like ant A and ant B, if they so they're going their way, right? And once they collide, A will switch directions, and so will B. But this was so where A is going now is where B was going to be going, and where B is going now is where A was going to be going previously, right? But since they carry the exact same properties, the titles A and B are fully arbitrary. So you can just like change the titles whenever you want. It doesn't matter, like, it's not like A is like unique in this way and B is unique in this way. They're all the same exact, they have the exact same features. So if I told you like, hey, they don't collide, they phase through each other and just keep going their original direction, well, what would that change, right? Absolutely nothing. If three ants are going on like some path, I told you previously, right? They're going, is going. When they collide, they change directions, or they collide, they keep going. It'd be the same because once they change directions, I'm just gonna take this other ant. Oops. Come on. So if they're gonna collide and change directions, now let's say they collided and phased. This ant will go this way. This ant will go this way, right? So my point is like, once they collide, it does not matter, right? It doesn't matter which one's which anymore. And A takes B's path, B takes A's path. So let's just rename A and B and say they didn't collide, they phased through. So we can throw away this portion of, what is it? Change directions. That doesn't matter. That's like it's trying to throw you off. The next portion is trying to throw you off is the going to the left or to the right. So what's happening here is they're saying, like, let's say there's some ants placed at N, right? And it goes to the left. The time it takes for it to fall off will be this length, minutes, right? Because 1 foot per minute. So it's getting placed there, going to the left. So what if it went to the right? If it went to the right, it would take 1 minus n. But in this case, couldn't we just say, hey, for the ones that go right, like they were placed at n and they're going to the right, let's just say, and they're going to take 1 minus n minutes. Let's just say, like, pretend land, that whatever time they would have taken is their actual location. As in, if they're going to take 1 minus n, put them at 1 minus n instead, conceptually, and move them to the left. We can do this because we're going to do this like for all of them, and so by symmetry, it'll be the same exact process. It'll be the same exact thing. If we take all of the ones that would have gone to the right and switch them left, it's gonna cancel out the differences, And it'll be the same regardless because they're all uniform. They can be put anywhere randomly. If we take one of the random ones and move it somewhere else randomly, it's still random. The random portion of this is that n. If we append the 1 minus to it, or prepend the 1 minus to it, it remains random because that n is the one that drives the randomness. And so we're gonna get rid of the left to right element of this conceptually by saying if it were to move, let's say it'll go to the left only. So all the ones that go right, instead of saying it's gonna start at n and go to the right, we're saying actually it'll start at 1 minus n and it'll go left. That's still random. And so we can conceptually go around the fact that they go to the left or to the right. Let's just say they all go to the left, right? Or the right. It doesn't matter which one you pick, but let's just get rid of that element of random direction. Okay, cool. The expected time for all ants to fall off the string will be the expectation of the max of x1, x2, x3 to x500. It will be the highest number. If we're saying they're all going to go to the left, right, conceptually, then the expectation of this will be the ant placed most far right, and that's the maximum. The ant with the most right starting point will be the max of all of the ants of where they're placed, the max of all the random variables. So the expectation of the max of the random variables is going to be equal to the integral across the support of the value of the support we're currently at, right? N, let's just say, times the PDF. Let's call this thing Z or something. It'll be the value of the support we're currently at times the probability at that value. So what is the probability at that value? The density, or not the probability density at that value. Probability density is the derivative of cumulative distribution. Because CDF, or cumulative distribution, represents a mass, and density is a derivative of mass. So if we take the derivative of the cumulative distribution function, we get to the probability density function. So the cumulative distribution function of z is going to be some function that tells us is going to be fz of n, and it says that z is which is equal to the probability of z being some number between 0 and n. It means that what's the probability of z being n? Z being n minus 1, z being like every value from 0 up until n. Probability of z being at most n, the max being at most some number, is a probability that, say this is n. The probability of z being at most n is equal to the probability of x1, x2, x3, etc., all the way to x500, all being at most n. Because if, let's say, x444 is like the highest number, we need that to be at most n, and every other number, for that to be the max, every other number must also be at most n. So the probability of this is the probability of, let's say, x1 being at most n, which is the length of this portion, because if we're from 0 to 1, then the portion that is allowed is anything from 0 to n. That length is called n, right? And n represents the portion of 1 that's allowed, right? The portion that's a probability generally is like or an event occurring, probability of event is equal to probability of success over total. Probability of success, or success over total, right? Success is n, that whole portion, and total is 1. So n, right? The probability that x is at most n, or one of the ants is at most n, is n. And same thing for x2. Same thing for x500. And so the probability that they all follow this criteria, since they're independent, we can multiply the probabilities together for them all occurring. And we get the probability, or this, equaling n times n times n times n times n 500 times, or just n to the power of 500. We said the probability density was the derivative of this, right? So PDF is CDF prime. So this derivative of this is 500 n to the power of 499. We said that the expectation function was this. So we're just going to plug in n to the power of 500 right here. Or sorry, 500 n to the power of 499 here. Factor out the 500. Combine the n values. And we get 1 over 501 n to the power of 501 from 0 to 1 times 500, which equals 500 over 501 minutes, right? It takes for the last ant to fall off. Cool, and that's the final answer. That's the end of the probability portion of the Greenbook.